My name is Garrett Hawkins, team captain of the BYU Mars Rover team, and it's my pleasure to introduce you to our 2021 System Acceptance Review. This year, despite a global pandemic, our team has created a platform with major improvements to our mechanical, electrical, software, and science subsystems.
A rocker bogie system, utilizing a differential bar, along with a minor redesign to the chassis, ensures good wheel-to-ground contact and stability across uneven terrain, while also accommodating enhancements to the electrical system of the Rover. The redesigned base station antenna is motorized and can be adjusted remotely. This year, the mechanical arm of the Rover has been completely overhauled. A SCAR design with a linear actuator decreases undesired joint play and allows for more accurate and dexterous control. The new design increases range of motion, allowing for a circular reach of 1 meter around the linear actuator, while still allowing for complete control of the end effector. What's more, the redesigned end effector is capable of lifting objects, both larger and heavier than its predecessor, ensuring that it will be capable of towing and lifting the requisite 5 kilogram payload for the extreme retrieval task. A newly implemented inverse kinematic software package automatically avoids obstacles in the arm's workspace. When large movements are necessary, the operator can use the software package to easily drag the arm to a desired position. When more precise movements are necessary, the arm can be controlled via an Xbox controller in real time. Student arm operators test the capabilities of the arm, as well as train for the competition, on a modular test lander that includes versions of the puzzles that will be encountered in the equipment servicing task. In order to complete every leg of the autonomous traversal task, refinements have been made to the Rover's localization and sensor suite. The addition of a real-time kinematic GPS system, utilizing a pairing of 2 GPS units, allows for the location of the Rover to be determined to within a meter of accuracy. A raw-spaced autonomous state machine combines input from all sensors, as well as user input, to determine how to proceed. It transitions between states autonomously and indicates its current state using an LED array located on the rear of the Rover. A refined AR tag detection system is able to locate and assess orientation and position of tags from up to 10 meters away. Upon identification of the tag, the Rover plans a course and progresses toward the goal, indicating success upon arrival using the LED array. In the Rover's electrical system, a new card edge design modifies existing PCBs in the Rover, allowing for more modularity, better cable management, and more effective cooling. A battery consisting of 65 2500 mAh cells powers the Rover, providing over 48 volts to the onboard voltage regulation system, allowing the Rover to be operated continuously for upwards of 2 hours. Additionally, an emergency kill switch is included, conveniently located on top of the Rover. The communication system utilizes a 900 MHz dual polarity Yagi antenna at the base station, and 2 linearly polarized antennas on the Rover, allowing for MIMO functionality. Coupled with on-Rover hardware accelerated video encoding, the system is capable of transmitting multiple high-quality camera feeds at low latency. This year, the science sub-team has created a new module that incorporates fluorescence, reflectance, and colorimetric techniques. The Rover's test suite allows us to quickly and accurately identify extant and extinct life on a variety of substrates in situ. A custom fluorescence microscope detects the autofluorescence of flavin-adenine dinucleotide, an enzyme ubiquitous in aerobic life. This technique consistently identifies extant life on rocks and in soil within seconds. A near-infrared camera is used to identify plant life by their characteristic relative reflectance of near-infrared and visible light. In addition, an onboard burette test determines the presence of proteins in soil samples. Dedicated augers and vials for each soil sample eliminate cross-contamination, and vials are designed to minimize the risk of chemical spill. Finally, to identify extinct life, geologists on the team remotely analyze samples via a stereo microscope and other cameras on the Rover in order to identify fossils and interpret rock fascias.
These improvements, along with a rigorous practice and mock competition schedule, will enable the BYU Mars Rover team to be more prepared than ever for the URC competition. Thank you for your consideration, and we hope to see you in June.